So firstly, welcome to the performance and capacity stream for this virtual conference. We've got 15, I think, well, 13 very good presentations and 2 from me. Actually, I hope you'll enjoy mine as well. Piara and Nathan will at various times be chairing the sessions. I'm chairing this one and actually presenting myself, which is an interesting challenge. And I'm hoping that Megan can admit anybody else who shows up because I probably won't see them at this stage. So anyway, good morning. zIIP capacity and performance. This is a presentation that has evolved over the years, and some of you I know will have seen earlier versions of this. I say evolve wisely because it's a topic where there has been news over recent years and there continues to be news. So I think this is an entirely valid presentation to still be giving so long as I try and keep up with that kind of stuff. And anyway, stuff does bear repeating, I hope. Please feel free to use the chat to ask questions. I probably won't see it until the very end. So just bear with me on that, because like I say, I'm chairing as well as presenting, and I'm not going to notice very much. So, okay, please let's go ahead. So some of these slides, because I've said it before, I'm going to do fairly briefly, but the meat of it I'm not going to do briefly at all. zIIP capacity planning is something that I think people don't pay enough attention to, even now. And as I say, this presentation has evolved over probably 5 or 6 or maybe more years than that. And people still aren't getting it right. And as I say, it keeps changing. So with a bit of luck, I will impart some knowledge here that you will find of some use. So this is my funky attempt at an agenda. So I'm going to give you 5 things that I hope you will remember. Actually, I hope you will agree with, or maybe you'll have your own views. A little bit on the importance of zIIP capacity planning, because just by showing up, I kind of think you think it's important anyway. Some really quite old news and some newer news. Then we're going to talk about the criticality of getting it right for DB2. Then we'll get into really the how-to somewhat. So this is where it gets a bit more serious. Then some performance topics and some miscellaneous topics, and then wrap up. And there is an appendix here, which is some stuff which former members of the DB2 SWAT team gave me. So this is John Campbell and Adrian Burke, who are now no longer, well, John has retired actually. And Adrian's no longer with IBM, but they gave me some useful backup material. I don't intend to present that. I do intend to present the bulk of what you see on the agenda other than that. So let's get into it. So let's start with the 5 things I'd like you to consider. Firstly, I think please take capacity planning for zIIPs seriously, because it's become more important. I think the message of paying a special attention to what percentage busy represents full, I think is kind of important. There is real value, and I want to spend a lot of time on instrumentation actually, on measuring zIIP potential and usage down to the address space level. I could say at this point that my other presentation tomorrow will be about architecture, and I think some taxonomy when it comes to zIIP usage versus things that don't is going to be useful, but actually I have some material on that in this presentation as well. I think you need to think carefully about LPAR design. That seems to be an emergent theme over the last 10 years anyway. I guess it's always been true, but even more so, and it's more complex now. And here's a key one. People will shove new zIIP eligible work onto your beloved LPARs. They may not bother telling you. This is the same old story, which is part of the reason for the architecture presentation too. People won't tell you stuff that they're doing. A lot of the new workload will be thoroughly zIIP eligible. And I've got some examples here, a little bit in depth actually, on some of the examples in this presentation. So those are the key points I want to get across this morning. Okay, so that I want to do the importance of zIIP capacity planning relatively briefly to make room for other stuff. So people really don't do zIIP capacity planning terribly well, or performance for zIIP terribly well, for a bunch of reasons, mostly around the economics of they're not nearly as expensive as general purpose engines, however you look at them. And typically their utilization hasn't been all that high. And the consequences for undersizing zIIPs, one would have said at one point, weren't disastrous. Now I'm shifting towards they are quite serious. So, you know, lazy people don't do zIIP capacity planning. People with very little time don't do zIIP capacity planning. I'm hoping, though, that just by showing up, you're in the self-selecting group of people who do think this is important, and other people really should. So, you know, it's not consequence-free, particularly these days, to run out of zIIP capacity. There's lots of logistics involved in this. And the new stuff is, as I say, increasingly likely to be heavily exploiting zIIP. And getting it wrong is impactful. One interesting footnote at the bottom here, I'm not sure if you can see my pointer, but anyway, batch window is an interesting time. It always has been, but it's even more interesting now because that often is a time when zIIPs get under stress for a couple of reasons. One is that's when people run utilities, and a lot of that work is zIIP eligible. And the other thing is people are running a lot more newfangled Java batch and XML processing batch and stuff like that. So I would say keep in mind the busiest time for the zIIP pool might not be during the day. It could well be, it might not be. As always, pay attention to the timeline. So I've said a couple of times now, things are changing. We're getting more zIIP exploiters. And actually what I haven't said yet, and I'm going to say it now, is some of those zIIP exploiters are more performance critical than some of the very early ones. So I'm not going to take you through the whole list here. I'm going to be talking quite a lot about DB2 from version 10 onwards. I'm probably not going to talk a huge amount about SMT, and I'm probably not going to talk about the rest very much, because these are quite old things that we will all have learned to roll with. The DB2 one, though, I think is so important that even though it's not new news, I want to spend time on it. Somewhat newer news. Again, you know, you may think that zOS 2.4 is new. You may not. You know, 2.5 has been out for almost 2 years, well, a year and a half now, hasn't it? So 2.4 not necessarily new, but maybe new to you in your shop. I know customers who are on 2.2, not many. I know quite a few on 2.3. You know, so moving to 2.4, 2.5 presents new opportunities. So zOS container extensions, or ZCX. See what I just did there, Z and Z in the same sentence, never mind. Hard to say ZCX, really. You know, that's something that may be in your future or in your present, hopefully not in your past. You know, we've got more things like high performance unload, sometimes using zips. We've got system recovery boost. So you might be, again, you might be on Z14 or possibly Z13. If you go to Z15 or Z16, system recovery boost is something that could well happen to /4 at you. We've got new funky stuff. Well, not that new, like Spark exploiting zIIP. This is kind of an interesting one. The zOS 2.5 WLAN managed initiators being sensitive to zIIP capacity, and hopefully I'll have time to talk to that point. You know, and so it goes on. And I haven't got zOS Connect on this list actually, and maybe the next iteration of these slides I will have that. More exploiters all the time, not necessarily widely trailed exploiters, but nonetheless ones that can drive capacity. And we'll talk about how to see what is actually running zIIP eligible and taxonomy in the presentation. But let's talk about DB2 first. So this is old news, but it's important news. So what's old but not but important news? It's commentary, I suppose. With DB2 version 10, deferred write and prefetch engines became zip eligible, and they are a substantial portion of the DBM1 address space's CPU. They're 100% zip eligible, actually. They have very stringent performance requirements, so they really must not be delayed, and they can't even be delayed to the point where you see the work crossing over onto general purpose engines. What tends to happen, in short, is if you run out of zip capacity, you're going to run out eventually of prefetch and deferred write engines, which are really SRBs, client SRBs, if that's meaningful to you, client enclave SRBs, in fact. And then nasty things happen, like we fall back to synchronous IO when we'd been expecting to do prefetch, likewise with the writes. So with version 10, the game changed. And we really especially must protect DB2 engines access to zip. GCP CPU as well, but especially to zip. This is 10 onwards, I will say. In fact, yesterday I was looking at somebody's WLM service definition across a bunch of systems in one plex, and half the systems only really have DB2 engine as the zip exploiter, and the other half have other things which are rather less performance stringent. It's interesting trying to analyze a situation like that when you know jolly well that you have to protect the only user of zip in some systems, but you can let other systems, other exploiters go to the wall a little bit. So this is a key one, protecting DB2 engine. So the blue here is really the key point here. Treat DBM1 as a key address space and protect its access to CPU. And you're probably saying to yourselves, I'll come back to this, I think, what about other address spaces in DB2 engine? Well, in version 11, the master address space becomes performance stringent. And at this point, even though the dist address space work that's zip eligible isn't the dist address space SRBs themselves, you might as well and probably should put dist in the same, let's call it STC DB2 or STC high service class with the same performance stringency as DBM1 and master. And 11, the reason why I got to this slide was because the master address space makes log write and log read zip eligible, which again is a performance critical thing. You don't want essentially to run into a situation where logging can't keep up. So just think of DB2 engine address spaces, DBM1, master, and zip as performance stringent on every axis, but particularly for the purposes of this discussion, protecting their access to zip. I'm going to see if I can actually go backwards. I'm not sure if I can. Yes, I can. Right. So I skipped over this one because the flow of this is different from how I presented this a little bit before. This is a standard way of graphing that I think you will find useful for any service class involving velocity. So here we have a service class called STC high. Footnote, this high priority STCs is not something I typed in. It is literally in the RMF SMF 72 subtype 3 record. And I've had fun in the past with the rubbish that people type in here, right? Because I automatically pump it out because the legitimate reason would be, so I know what STC high is as if I didn't already know it's high priority STCs, at least rhetorically. Like all comments in code, it's only as good as its own accuracy, right? Which is highly variable, isn't it? Anyway, the green here is the velocity goal for the service class, which, as it says here, again, auto-generated from the data, is 70% velocity. Along the x-axis here, what I have is the general purpose engine CPU utilization for the service class in this system. And this is not centered because I've obfuscated or taken away the actual SMF ID, right? Now, each of these data points is a different RMF interval. The different color blobs and shapes is for different dates, right? There's a clear trend here that when the utilization is low, the velocity obtained is pretty darn high, pretty close to 100%. But obviously, from the slope of it, you can see if workload built up, the velocity obtained would go down and would continue to go down. So say this is a general purpose way of graphing velocity attainment versus goal against busyness, whatever we mean by busyness. Now, the key thing here is you don't really want this, if it's containing DB2 engine, to be slowing down. The likelihood is, particularly with IO priority management enabled, that it's slowing down because we're getting delay for CPU and quite probably delay for zip. So this is a useful depiction of a not particularly protective goal of 70%. Now, if you're going to persist with IO priority management, and there is a presentation from a friend of mine in this virtual conference on that whole subject, you probably need a goal higher. You may well want to pull DBM1 and master out of STC high into their own service class with a higher goal. This is a bit of an art form working out exactly what to do, but those are the sorts of thoughts I would have. So if I go past 11 and into 12, I can do this incredibly quickly. There is yet more zip eligibility in DB2 engine, varying degrees of criticality, though some of this stuff is very critical. So the message protecting DB2 really doesn't change. The detail gets enhanced, but the message doesn't change. Okay. The next point to make is that DB2 engine itself is sensitive to IIP on a priority. The key point here is if IIP on the priority is set to no, then DB2 won't even try to use zip. And then we're into how do you protect DB2 engines access to GCP CPU, right, for both master and DBM1. Hasn't got anything, by the way, to do with DDF enclave dist zip exploitation. That's a completely separate thing. So just be a bit careful about IIP on the priority. Now, by the way, it is only checked at the system level, and it's checked at DB2 startup. If you are doing IIP on a priority yes, and then disabling it at the service class level, that's not the check that DB2 engine is doing. And another point to make here is SMF30, one of my favorite SMF record types, as I think you'll see in a minute, and actually in my other presentation, will tell you, if you ask it correctly, what the regime is for DB2 engine address spaces. So you can do the analysis, you can know what's happening. And actually, as you'll see in a minute, you can tell how much zip CPU the DBM1 address space is even using. And if it's nothing, then that's an obvious red flag. Okay, so I've given you the obligatory lecture on DB2 engine protection. Let's start talking about instrumentation a bit more, and I've already given you a little bit of that. Okay, so in this game, the main sources of information are going to be, firstly from RMF, SMF 70 and 72 subtype 3. So that's system level, machine level in the 70 case, and 72 subtype 3, workload service class, report class level. From ZOS itself, SMF 30, as I previously mentioned, SMF 113 and 99 subtype 14 at the processor level, which I will touch on briefly. And from middleware, and now this is where ZOS Connect probably should be added to this, particularly from DB2 and from Kix, we've got the accounting trace for DB2, SMF 101, another one of my favorite records, and then SMF 110 Kix statistics trace. Give some information at the middleware level. And for products that use zip and use the IFA usage macro for usage pricing, SMF 89 subtype 1 includes zip usage by product in the usage data section. By the way, and I'm not sure this is later in the presentation, SMF 30 doesn't have a companion field in its usage data section for zip usage by product. And just a footnote here, SMT adds considerably to the complexity of the metrics. So let's start at a high level with at the machine level, really. From SMF 70 subtype 1, you can see how busy the zip pool is, just like you can with the GCP pool and sort of with the ICF pool and with the IFL pool, right? So this is just a diagram that says, look, you can see the dynamic day on day. Some days are busier than others. The shape is generally the same. Not necessarily a particularly interesting example of a day-on-day analysis. Interesting, this is 2013. I'm going to have to guess who that was because that's a long time ago, isn't it? Equally from partition data, this is summing up all the partitions, by the way. This on the right-hand side is breaking it down by partitions. So you can see one partition in particular, whoops, is considerably bigger user of the zip pool than the rest. And that's a fairly basic thing to feed into the LPAR design considerations you'll undoubtedly get to. 72 subtype 3, and I probably should change the color on this one. You can break down the zip usage by service class or report class. This particular case, by the way, is zip eligible work that actually ran on a general purpose engine or general purpose engine pool. So here we got STC medium is the one with all the eligibility for zip. So this is, I just want to introduce the idea that you can do zip on GCP, which we'll talk about again later, as well as zip eligible work running on a zip. Okay. A sidebar, which I think will be useful, and we'll kind of explain that deterioration of velocity earlier. The way we calculate velocity, and this is not my calculation, this is the standard calculation, is to take all the using samples and divide them by the using samples and the delay samples, whatever category those actually are, and turn them into a percentage. So that's how we do a velocity calculation. Now, the reason why I rehearsed that formula is because I want to talk about what the samples actually are. So for velocity goal service class periods, you get, as I say, samples. Let's park the whole zip thing for a second. For work that's not zip eligible, you get using and delay samples for things like CPU and IO. And those are the primary ones, general purpose engine, CPU, in fact, and IO, right? These are the sample counters that affect the velocity calculation. I will at this point say if you turned off IO priority management, IO won't be in the using and delay samples calculated to drive the velocity calculation. However, one thing we do is we do the alternate calculation, turning off IO samples or turning them on depending on what the system under study is not doing. Now, with zip eligible work, you get more samples. You get using and delay samples specific to zip. That could be, and the next slide I think is a fairly poor example of this, to be quite frank, could be useful to correlate delay for zip with percent of zip eligible work that's ending up on a general purpose engine. Could be, but it's a bit more complicated than that. So some notes on this. General purpose engine samples actually include the zip eligible work that ran on general purpose engines. So you have to subtract out the zip on GCP to get, as we now do, GCP only work running on GCP, or work that was never eligible for a zip that ran on GCP. So there's that small gotcha. You may end up with double counting if you're not careful. I will say, in fact, that for CPU-like samples, the using is based is based on time rather than actually sampling. I will say, and this is kind of back to why this correlation is a bit fraught, 0 zip on GCP number is not necessarily a sign that all is well, because it could be we couldn't get the needs help mechanism to work because general purpose engine pool was equally stressed. Equally, work with the zip AWMT mechanism could still be delayed for zip, but ultimately run on it, and it wouldn't show up as zip on GCP under those circumstances. So be a bit careful with this. The numbers aren't necessarily quite as straightforward as they might appear. Conversely, non-zero work that's zip eligible running on a GCP might not indicate a problem. So, for example, there are some ZOS locks that make the waiter run on a general purpose engine. So that will show up as zip eligible, but running on GCPs. So careful with the numbers here when it comes to sampling, but they are generally a useful way of carrying on. Okay, I'm probably going to skip this one, I think. Oh no, just very briefly. As we'll see in a bit, DDF work, which is what this service class is, tends to split 60-40 zip eligible. So this is the blue, zip on zip, and general purpose engine on general purpose engine. So 60-40 zip to GCP. The green here is actually zip eligible work that ran on GCPs. Okay. So it's quite a nice stack up. You don't necessarily need to graph this by time of day, but it's just an illustration of the point using the samples. And actually, to be fair, that's a slightly older version of the graph than we use nowadays. Now, the next key point is it's worthwhile understanding your exploiters, not just to understand the high stringency CPU stuff like DB2 engine versus the rest, although I think that's kind of important. So exploiters come in different shapes and sizes. I kind of think of it as our equivalent of the particle zoo. Coming in different shapes and sizes, they leave different footprints in the data sand accordingly. As I say, they likewise have different criticality levels, which, to repeat the point, really ought to be reflected in your workload manager setup. We have dependent enclaves, whichever way you want to pronounce them, and some of you will probably pronounce them again differently. Over a beer in Atlanta, I'm sure at least one of you will tell me how she pronounces it. Dependent enclave. Best examples of these are DBM1, prefetch, and deferred write engines that we've already talked about. Right? That runs in the address spaces service class. Independent enclaves, for example, DDF work, runs in its own service class, independent, hence the name, of the address space it's running in, which would be the DB2 dist address space. Then we get really what I should call the rest, which is really ZAP on zip, which is former ZAP eligible exploiters, such as Java, not JNI, but such as the rest of Java, that would have run on ZAP if we still supported ZAP, but now run on zip, and very similar things that are inherently zip enabled. So an example of this, as I say, just to labor the point, dependent enclave for DBM1 address space is performance critical from DB2 version 10 onwards. And that's a key piece of analysis. How much of that have I got? Now, normally when I present this is an eye test. You can possibly read it. This is just quite an old example now of a fragment, because it's now the list is much longer, of address spaces with zip eligibility classified. So down the side, you can see the job name and program name, and these subtitles are really different service classes within workload STC, it turns out, STC high and STC medium, and vaguely useful, in this case, very useful, report classes. I'm getting hotter, by the way, on good report class structure, because I think that that can really help people getting it right. And so many people get it wrong. And this one, STC CAUTH. Now I'm thinking this is Kik's other. Well, we've only got 8 characters, so they've used 7. That's not too bad, right? Let's take the bottom one first. So this is a bunch of Kik's transaction gateway address spaces. I know it because the program name is CTG batch, which is mnemonic. And in my architecture work, I will use that as a mnemonic for CTG. And here's the address space names. Here's the TCB time. Here, by the way, this is all zip on GCP because this customer did not actually have zips at the time. So this is the headline number. And here we see all of it is in the other category because CTG is basically running Java with presumably some JNI. Hence the 0.12, despite the nastiness of rounding here, not helping us realize there's a bit of a difference between this and this. Compare and contrast that set of footprints in the sand with the DB2 engine. This is version 10, where we've got all, for DBM1, all the zip on GCP work is dependent enclave. As I say, defetch. It's a good contraction, isn't it? Deferred write and prefetch engines, as opposed to the dist, where all the CPU that is zip eligible is in independent enclave. So that's exactly what I said before, but this is an example of it, albeit old, but I think it's useful enough to persist with this one. You can very readily do this analysis however you crunch your SMF30s. And as I say, we've got a bit more granularity here than just using the report class, because in one case, DBM1 is using dependent enclaves and the dist address space is using independent enclaves. And guess what? I would expect master would show up here doing, again, dependent enclaves. Okay, so that's a piece of taxonomy. Another thing very briefly to mention to you is the proportion of, let's say, the DBM1 address space that is zip eligible will vary depending on what the DB2 subsystem is doing. So here, we have a drop in zip usage, and we actually have a drop in zip percentage of the total CPU used by the DBM1 address space. I'm not saying this is something you should routinely plot and examine, but getting some idea of how much zip eligible work as a proportion, how it might vary by, batch, which might have more prefetch and deferred write than, say, online transactions does. That's a kind of interesting thing to do. Obviously, as I've said before, as you go up through the DB2 versions, an even higher proportion is zip exploitative. And I've already mentioned the point about the amount that is zip eligible will depend on what the work profile actually is. This presentation has capacity planning in the title. I'm going to nod in the direction very briefly because there's a couple of points that are worth making about projections. So near term, if you like, zip projections, for existing workloads that don't run on a zip, the project CPU mechanism, which we've already seen in action with the zip on GCP numbers, reports how much CPU is zip eligible via RMF at the service class or report class level. Actually, we get it from type 30s as well. Now, if you were moving up from version 10, which most of you probably aren't now, I think a reasonable course estimate would be, well, the rest of the GCP CPU is going to be zip eligible. Not 100% true, but pretty close. Now, In the short term, if you have a new workload you know nothing about because it's not there and therefore you can't measure it, you'd have to use any sizing guidelines you can get. Probably in test, you all have robust test environments, don't you? Of course you don't. I know that's unrealistic for many of you. In fact, almost everybody. Be careful with the protect CPU mechanism, because there are some exploiters that I would consider adaptive. So if you have a zip, they'll use it. If you don't have a zip, they'll not try to use it. So project CPU will show you nothing for those cases, right? And this is why I cop out completely and say, from the point of view of capacity planning, projecting into the far future or medium future is just the same for zIIP as it would be for GCP. So whatever methods you use for forecasting from those points of view probably are good enough, and the only thing you can reasonably do for projecting zIIP into the future. But for the near term, the rest of the slide applies. Okay, some performance things now. One of the key things I want to impress on you is you need some care over LPAR configuration. A lot of customers I work with give zIIP access to LPARs where you could say that probably wasn't a great idea, because they're they're not delighting anybody. They're diluting access to zIIP to the LPARs that really should use it. Now, you could say not enabling an LPAR to have access to zIIP is leaving money on the table. And the answer is, yes, I know. But you have to make the trade-off to understand whether that's actually what you have to do to enable within your zIIP pool other more deserving LPARs to have better access. Of course, what IBM would like you to do, of course, is to buy enough zIIP not to have to make those sorts of decisions. But pragmatically, people do have to make decisions about LPARs where, frankly, the zIIP exploitation is minute, and giving share or even logical zIIP engines to the LPAR hurts LPARs where it really should be given to. So that's the first point. The next point is that LPAR weights need a special care. So, for example, the need help mechanism works best where it's a vertical high logical zIIP that's asking for help in a timely fashion. Because vertical mediums or vertical lows might not invoke the needs help mechanism soon enough, particularly for the stringent exploiters. And so it gets particularly painful if you think about the case of, so if an LPAR can't have a vertical high zIIP, should it have a logical zIIP at all? And the other thing to point out here is the obvious, which is weights are a zero-sum game. If LPAR A has too high a weight, it might well prevent LPAR B from having a high enough share to do the things I've talked about so far. Another thing to think about is if you have super large LPARs, then zIIPs dispatched in another drawer are likely to affect the processor cache effectiveness, not just of the zIIPs that's dispatched in the first drawer, but also general purpose engines dispatched in the first drawer. And running on vertical mediums and vertical lows, actually this is not particularly zIIP specific because it's GCPs as well, increases the risk of dispatch on a different drawer with the cache damaging effects that can bring. So LPAR design in any case is important. And as I say, running on vertical mediums, vertical lows increases the risk of cross-drawer dispatching, and obviously multi-drawer LPARs do too. And you might well find that most of the time you're running with your LPAR running happily within a single drawer, but unpark some vertical lows and suddenly you're running cross-drawer. So this sort of stuff needs careful analysis and thinking about. zIIP short engine effect is really a case where you have relatively low zip usage sharing a zip, and there's potentially a high latency in that logical zip being dispatched. Well, really, that's most poignant when other LPARs are competing effectively for the zip. Now, hyperdispatch does its best to try and help with this sort of thing, but there's only so much it can actually do. So I'm really particularly, again, concerned with small LPARs, single zip LPARs with low weight, and particularly the compounding factor where the primary or only thing really wanting to use zip is going to be DB2, DBM1 engine, well, or master for that matter, DB2 engine really. Because there, nobody else is going to take the early bath. It's going to be the DB2 engine that is going to take the early bath. So under those sort of circumstances, again, you might consider not configuring the zip, a zip to the LPAR at all. LPAR design being a bit tricky. Okay. So we have somewhere between 15 and 20 minutes left. I want to talk about some other interesting miscellaneous topics. Let's talk about service class level IIP on the priority. These APARs will, almost everybody will have the fixes on for them. So the idea here is it prevents crossing over from zip to GCP for the service classes that you nominate it for, specify it for. It's designed to protect the general purpose engine pool from large zip exploiters such as Spark, which is thoroughly zip eligible. That can cause a lot of CPU, so you probably do want to protect against a burst of Spark work or similar crossing over onto general purpose engine pool. By the way, the same mechanism allows you to memory cap these address spaces. SMF30 actually has a flag for this, obviously at the address space level. You could be choosing to apply that to non-Spark work as well, but with a certain amount of caution. Maybe it's Java batch. That's another possibility. It could be a useful tool, is all I want to say on this. But just to repeat something, this does not affect DBM1 test for the ability to cross over. That's the system level variant. Okay, let's talk about ZOS container extensions, or ZCX. ZOS 2.4, Z14, or later hardware. Essentially, it allows Linux on Z containers for Z to run on ZOS. These are really Docker containers initially. This is an old statistic. I don't have a more modern one, but this is a nice enough one. You know, that there are a lot of Docker images around that could run in ZCX. It contains enough Linux and Docker infrastructure to run the containers. You can have multiple containers or application instances running in a ZCX address space. You can have multiple such address spaces per LPAR. And the point about those two is there are architectural decisions to make. So, for example, do you put a 500-pound Gorilla one in with a load of tiddlers? Do you run one application per ZCX address space? And you'll see why in a minute that might not be a splendid idea in all cases. You know, how do you mix and match these? I think is kind of important. And I think with the OpenShift, this is probably the only time I'll use that word in this presentation, possibilities, you know, this is going to become more popular. And it could happen. I'm going to say this in a way that people might find a bit insulting. It can happen to you, meaning somebody puts up a load of these address spaces and doesn't bother telling you as a performance or capacity person that they've done it. So this is one to keep an eye on and keep, again, reporting is key to everything here. They have a high level of zip eligibility, hence you'd better know if they arrive and measure their impact point. Again, you might want to limit their access to GCPs or prevent it for the zip eligible portions using IIP on a priority at the service class level. If these applications talk to DB2, they could well have a knock-on driving effect on DB2 zip usage. So you need to know if ZCX is going to happen. And no, I don't have a downer on it. I just think it's significant. It's a good example of a significant new user of zip. You define how many virtual CPUs in the parlance each address space has. These map onto TCBs, but are seen as processors by the Linux infrastructure. And these control access to zip. So, you know, if you have 4 engines or 4 virtual CPUs, they could use up to 4 zips or 4 zip threads anyway, if we were talking about SMT. I'm throwing in gratuitously a couple of APARs that Nick Matsakis and Anthony Giorgio mentioned to me, because they're kind of important for the performance of this, and you might as well know them even if this is supposed to be about zip. So initially, they used 4K preferred fixed pages to back the storage. There's an APAR here, which now does a couple of things. One of them is it includes large page support, and this is long-term page fixed storage starting at 2 gig minimum per address space. So nice characteristic there, lots of storage, long-term page fixed. This API introduced the ability to use large page frames, so 1 meg and 2 gig frames. It also introduced some other zip optimizations. Now, if you've downloaded this presentation, this is a live link to a nice paper by the pair of them. Right. Also, one thing worth pointing out is with this APAR, in general, about 95% of the processing done in ZCX will be zip eligible. Okay. I've also made the mention of the 2 gig minimum, and that's probably a very bare minimum for an address space. Hence, my comment, you might not want to give every application its own address space, and it may not be 2 gig, it may be 4 or more. One note here, if you happen to be running on an LPAR with more than 4 terabytes of storage, as of 2.5, because ZCX can use 2 gig pages, if they do, those pages can be above the 4 terabyte, I don't know what we want to call it. We've had line, we've had bar, what on earth you call it, I don't know. But anyway, above 4 terabyte real. So that's a possibility for some. And here's a live link, planning for ZCX memory considerations. Another APAR here with some scalability and zip eligibility increases, particularly for larger address spaces. So the more virtual CPUs, the greater the benefit. Context switching is one of the things that kills zip eligibility and performance in general. And this APAR, one of the things it does is it gets rid of almost all of the context switches from zip to GCPs. So saving path length and giving more zip eligibility. And some COM server APARs that also have a positive impact and actually increase the zip eligibility. So you almost certainly will have this maintenance on. One of the things I like to say, and as an old-fashioned SE, it's probably part of my marketing DNA to say it, is ZCX you shouldn't think of as one and done and therefore ignorable. It's something where there's continuing effort and continued effort in refining. And these are some examples. This wasn't meant to be a marketing pitch, but I think you need to be aware of these, particularly as they affect storage, but as this is a presentation about zip, they affect zip too in a positive way. Okay, let's talk about DB2 again briefly, because I have a nice example coming up. DB2 accounting trace, SMF 101, gives you some very nice sets of numbers on zip eligibility and categorization below that nice grid I showed you earlier with the CTG batch address spaces and the DB2 engine ones. And by the way, my DB2 DDF analysis tool, which is open source and licensed under an MIT license, reports on the zip eligibility and usage using the accounting trace for DDF. Free advert there, Martin. Okay. Now, this is a nice example. Now, I mentioned earlier that you should expect most of the time, I didn't say it in quite as detailed way, DDF work to be about 60% zip eligible, 40% not. What you can do with DB2 accounting trace for DDF is actually understand why you might be getting less zip eligibility than 60%. The way you do it is you turn on package accounting, which is IFKID 239 as opposed to IFKID 3, and then you look at the individual packages. And if you do that, you get something like this. This is a real customer example. I actually remember who it was, and it was the last but one customer before COVID hit. And I know where I was when I presented this. Happy days. Along the bottom are the names and classifications of things. Obviously, I've obfuscated most of the names. The orange, almost said red, I don't know why. The orange is zip eligible. The blue is not zip eligible. So here we have an example where almost none of it is zip eligible. And this is a stored procedure. And this is a non-native stored procedure, meaning it runs in a server address space. So typically that means additional application logic over what SQLPL will allow. Those are not zip eligible even coming from DDF. Hence the very small zip eligibility. This, though, is a native stored procedure running in the DBM1 address space. And you can see it's got 60%, roughly speaking, zip eligibility versus not. I won't labor the point. This package here, by the way, is not a stored procedure at all. And there are flags for whether a package is stored procedure or not in the accounting trace at the package level. The point of laboring this is to say to you, if you're not getting 60% zip eligible for a DB2 DDF workload and you expect it, you can do the analysis to say, this is a non-native stored procedure. That's why I'm not getting the 60%. Then what you do is you say to whoever's responsible for this, I know this is unlikely, but is it possible this could be reworked as a native stored procedure? If the answer is yes, then that might, the CPU saving or the GCP CPU saving might be the impetus to go and do it. So I'm going to skip this one, I think, and this one, and this one. So I want to talk about system recovery boost and leave a little time for questions. So system recovery boost allows zips to run non-zip eligible shutdown and restart work. At least this is the initial iteration of it, during a specified boost period with no impact on IBM software cost. It also allows, if you have them, sub-capacity GCPs to run at full speed. There is a feature called SRB Upgrade, which if you sign up for it and it's money, allows deployment of extra zips. Now, one key thing is, if you're on Z15, Z15 or Z16, you may well already be doing SRB IPL boost. You might choose explicitly to disable it, but it's on by default. There are other boosts where you can optionally have the boost called recovery process boosts, and those provide short-term acceleration for specific recovery events in ZOS. Now, one key thing here, this is the reason for even including it, is during a boost period, an LPAR, maybe that should be a LPAR, I don't know, but that doesn't sound like English. An LPAR could use a lot of zip. It could use a lot of zip to the detriment of another LPAR if the other LPAR's share is not set up sufficiently to protect it. So this puts even more emphasis on getting the weights right for LPARs. Now, having said that, what I've just said could be true for any large surge in zip eligible work. So for example, utility window could knock another LPAR zip access sideways, right? But I think for system recovery boost, particularly because you may not have noticed it's on, you need to think about this. You need to think about this anyway, but that's a particular case. So some points on this. You need to assess how you choreograph shutting down and restarting an LPAR, actually an unrecovery process boost as well. Because exploited, and I think this is a good one, it could potentially increase the parallelism of shutdown and IPL and reduce the turnaround time. So by the way, I think it's time we had an update of the mean time to recovery red book. Pious hope that one, but maybe one day we will, because I think this is a bit of a game changer. You need in particular to assess your automation for shutting down and restarting, maybe around SRB's messages, possibly using the IAEA shutdown boost start procedure to activate shutdown boost, because shutdown boost won't happen unless you actually ask for it explicitly. Now, me being a nosy perisher, I know in the data if there have been SRB events, because most customers have got this APAR and subsequent ones on. So the RMF product section for all SMF 70X record types tells you if this LPAR has SRB happening and what kind. It doesn't distinguish, by the way, between different types of recovery process boost, but it does tell you if it's a recovery process boost versus shutdown versus IPL. And actually, we will end up with a new interval when there is a start and end of a boost period. So that may do funny things to your reporting. Nicely, in SMF 70 subtype 1 partition data section, you will get an indicator if any other LPAR on the machine experienced a boost. So that might explain to you what just happened to your beloved LPAR when its access to zIIP got curtailed, for example. This is very nice, actually. All of this is very nice. Could be very slightly nicer, but it's very nice. And so part of the reason I'm telling you this is there could be a lot of zIIP, and part of this is because you can actually see in the data SRB in action. Okay. Okay, I think I'll probably skip this because I want to get to WLAN managed initiators because we're very short of time now. Prior to ZOS 2.5, WLAN managed initiator support didn't take into account zIIP capacity, whether to start initiators and where to, because that was all based on GCP capacity. Now, 2.5, it's possible to have WLAN managed initiators take into account zIIP capacity. As I said before, increasingly common to see zIIP usage spikes in the batch window. So ignoring zIIP usage is possibly not what you want to do. The recommendation from development is you have separate service classes for zIIP and GCP. I don't think that's terribly realistic. It's worth considering if you can do it, right? You know, how realistic is this? Multi-step jobs, well, some steps might be Java and some steps might be DF-SORT. So can you really separate that job into two? Not really. You wouldn't re-architect into separate jobs to do that. I'm not a big fan of proliferating service classes. This already happens way too much in my experience for batch, for WLM managed versus non-WLM, for example. So the other point to make about this before I finish is WLM isn't clairvoyant and only knows about recent service level statistics. It doesn't know what a job is going to do. Right? Again, it's a bit like WLM managed DB2 stored procedures server address spaces. It's not an accurate prediction. It's using statistics to attempt to understand the work coming at it. So this might well be useful. It might be very difficult. Okay, just to wrap up, capacity planning for zIIPs has become much more important. Pay special attention to what percentage busy represents full, because it's probably lower than for GCPs. I've shown you how to measure zip potential and usage down to the address space level, and that's a useful thing to do. Consider your LPAR configuration carefully for zips and be aware of new exploiters and changed in nature exploiters because they can significantly change the demand for zip. So those are things I really wanted to get across. Some of those will be very familiar to you. Some of them may be slightly less so. So I'm going to see if there are any questions. We are officially almost out of time. Okay, so if you have a question, please ask it in the chat right now. Then any hurry in getting off the mic is basically to enable the next session, which is actually one I'm chairing anyway. But if you have any questions, please ask them now. I'm very happy to entertain them. Otherwise, most of you, I think, know how to get hold of me. Okay, I'm going to assume there are no questions. So I will say thank you very much for your time. And it's very, very good to see so many of you show up, and particularly some old friends, not so old, they would probably say, from various parts of the world. So the next session will be at 10:30 UK time, which I will be chairing, but I won't be speaking much. All right, talk to you all in a bit. Bye for now.